Which of the following is true about semiconductors? A. Number of charge carrier in semiconductors decrease with temperature. But this is not true because the number of charge carrier, the holes and the electrons are increased as the temperature increase, do not decrease with the temperatures. Alternative B says, at a certain temperature, semiconductor have both positive and negative charge carriers. In semiconductor, with increasing temperature, electron gain enough energy to jump from the valence band to the conduction band, creating free electrons, the negative charge, and the holes, the positive charge carriers. Therefore, at certain temperature, both types of charge carriers are present, that is, the negative and the positive charge carrier are present at certain temperature. So this statement is true. When you come to alternative C, conduction in semiconductor is due to free electrons. This is not always true because the conduction in semiconductor is not only from the free electron, but it also includes the holes, that is the positive charge carriers. Alternative D says semiconductor has a positive charge carrier. Yeah, it is still true, but not only a positive charge carrier, but also has a negative charge carrier. But the correct statement concerning the semiconductor is on alternative B. At certain temperature, the semiconductor has positive and the negative charge carrier. So the correct answer is on alternative B. So the diagram indicates that an input of alternating current to a black box and the resulting output of the current is this one. Then what will be these black boxes? So this is the image of rectification, that means converting alternating current into the directing current. So directly the conversions of an alternating current into direct is occurred by a device which is called a rectifier. Rectifier is a combination of a diode. We can use either a single diode as a half-wave rectifier and a 4-diode as a full-wave rectifiers, which is we call the bridge circuit. So if the diode is inserted in a source of alternating current circuits, we have one diode here connected with the resistor. So these sources of alternating currents are AC sources. The graph of these AC source become, if the current is forward, that means the diode is forward biased, then the current is produced in the diode. And if the current changes its direction, that means alternating current continuously changes its direction as a forward, backward. So if the current is forward, we have the current passing through the diode, so the current flows through the resistor R, and this is the diode. But if the current changes its direction or reverse it, the diode do not allow the current to pass through the circuit, so the current is blocked. So we don't have the current here, zero current is. And again, if the current is changed its direction and become forward, we have the current, and if the current is reversed, we don't have current is zero. So we get something like this diagram. So we have current is in the reverse bias, no current. Again, forward bias, we have current, and reverse bias, no current. Forward bias, we have a current, and this graph continues like this. So this is what we call the half-wave rectifier, half-wave rectifier, or half-wave rectification simply. So if the capacitor is inserted with the diode in this circuit, we have a filter. If the capacitor is inserted, we have an AC source, a diode, and a capacitor C is inserted in the circuit like this, and this is the resistor, and this is the diode. So this is AC source. If the current is moving forward, the current I is moving forward, we have the current here, and the current is start to flow through the circuit. But if the current changes its direction and reverse it, the diode do not allow the current to flow through the circuit. So this circuit has no current, but at this time the potential difference across the capacitor start to push the charges on the capacitor to flow and continue current through the circle. So at this time the capacitor is using as a source of an EMF, since the potential difference across this capacitor push the charges on the capacitor and make it flow through the circuit and make a current. So at this time there is a current is moving through the circuit smoothly. smoothly, but the current reduces with time because the capacitor is discharging. And again, after some time, if the current forward, we have the current flowing through the circuit like this. That means the current is flowing and the capacitor is recharged again. If the current is changed the direction, the capacitor helps us as a source of EMF because potential difference across the capacitor push the charges again to flow through the circuit, and it continues like this. So the diagram indicated is directly the black box is a diode with a capacitor filter. That is the correct answer is on alternative D. The kind of graph which has this form is when capacitor is inserted with a diode in an alternating current circuit. So the black box must be the diode with a capacitor filter. So depletion layer or depletion zone is an intersection between p-type semiconductor and an n-type semiconductor. When p-type and n-type semiconductors are combined together, the intersection between them forms what we call a depletion layer or the depletion zone. So n-type semiconductor has an excess number of electrons and p-type semiconductor has an excess number of holes. That means positive charge carrier. At the depletion zone, some excess electron jump from n-type to the p-type and left the hole here and form some extra electron in the p-type, and the holes extra holes are left in the n-type. So this is what we call the depletion zone. In diode we have one depletion zone. That means we have one depletion zone or the depletion layer. When we come to the transistor is also the combination of p-n junction. So we have two possibility, p-n-p and n-p-n. That means two p-type semiconductor and one n-type semiconductor combined together and to form p-n-p transistor. And also we have a possibility two n-type semiconductors and one p-type semiconductor combined together and gives us a n-p-n transistor. So in transistor, the intersection between p and n has a one depletion layer or one depletion zone, and also again here we have the intersection between p and n junction, also another depletion layer. So here also we can consider one depletion zone. This is also another depletion zone. So in transistor we have two depletion layer or two depletion zone simply. So the correct answer for this question is on alternative B, which says the number of depletion layer in transistor is 2. So the objective of adding impurity to a semiconductor is to increase its conductivity. That means that in the other case, to decrease the resistance of the semiconductor or to decrease resistance of the crystal. So the main objective of adding impurity to a semiconductor is to increase its conductivity or the conductivity of the crystal or the material, or to decrease the resistances of the material. So the correct answer for this question is on alternative C, which says to decrease the resistance of the crystal. The emission of conduction electron from the hot metal in a diode valve is known as, so it is obvious, it is called the thermionic emission. Thermionic emission. So thermionic emission means that when the high voltage is connected to the vacuum diode or a vacuum device with a cathode and anode, that means a negatively charged electron which is connected to the negative terminal of the sources and anode is connected to the positive terminal of the source, and the heater or electric heater is heated the cathode. So as this cathode heats, the electrons start to emit from the surface of this cathode and attracted toward the anode and flow like a beam of light, is which we call the cathode rays or a beam of electrons. So this process is simply known as a thermionic emission. So the correct answer for this question is on alternative B. So the diagram given is a combination of 3 logic gates, the 2 NOT gate and 1 NAND gate. This is NOT gate and this is also NOT gate, but this one is NAND, not AND. So just we can do the truth table for this combination of the logic gates. That means which one of the following is equivalent to the above combination. So according to this diagram is equivalent to which gate is it AND or NOR or the NOT gate. So then just we can prove this by using the truth table. This is the truth table. We take A as input 1, B as input 2, and this is the output from A and B. The resultant output is this one. And if I do the truth table for this, you know that we have 2 input. If we have 2 input, our truth table must have 4 rows. That means we have 0 and 0, 0 and 1, 1 and 0, and 1 and 1. To determine how much rows we need, the number of rows must be to the power of n, where n is the number of the inputs. Since we have the 2 input, so the number of row is equals to the power of 2, which is 4 rows. But if we have 3 inputs, to the power of 3 is equals to 8, so we have to have 8 rows of the table. And if we have 4 input, then the number of rows become to the power of 4, which is equals to 16 rows needed. So in this case we have 2 input A and B, so we need to have only 4 rows, 1, 2, 3 and 4 rows needed. So since the 2 first gates are not 0 means at C we get 1, and at D we get, which is not 0 means still we have 1, not 0 is 1, not 1 is 0, and not 1 is still 0. But at point D or at output D we have to consider the input from B, that is not 0 is 1, not 1 is 0, not 0 is 1, not 1 is 0. So the output must be, output is the input from C and D, and the output must be, it is considered as a NAND gate. So we have to consider C and D combination. So 1 and 1 is 1, but the NAND is the opposite of AND, so we can consider 1 and 1 the opposite one. So 1 not AND 1 or 1 and 1 is the 0. 1 and 0 is 0, but the reverse is 1. It is NAND gate. 0 and 1 is 0. The reverse is 1, and 0 and 0 is 0, but the NAND is 1. So this is the output we get. The output we get is 0, 1, 1, 1 for the input, 0 and 0, 0, 1, 1, 0 and 1, 1 from A. But if we do the OR gate, this OR gate from A and B, 0 or 0 is still it is 0, since we have OR. 0 or 1 is 1 for OR gate. 1 or 0 is 1, 1 or 1 is still 1. And if we do for AND gate, is 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. But for NOR gate, NOR is the opposite of OR, so the opposite of 0 is simply 1, the opposite of 1 is 0, opposite of 0 is 1 is 0, the opposite of 1 is 0. NAND is simply the opposite of AND, so we have the opposite of 0 is 1, opposite of 0 is 1, opposite of 0 is 1, and the opposite of 1 is 0. But if we consider OR, AND, NOR and NAND with our output, is which one is equivalent to the output? Easily we can see that here we have 0, 1, here 1 and 1, 1 and 1, 1 and 1. So the output is equal to the OR gate. So our circuit or the combination of the logic gates are equal to the OR gate. So the correct answer is on alternative B. So if the diode is forward biased, it is obvious that diode is a combination of PN junction or PN type semiconductor combination is what we call the diode. So if the diode is forward biased, that means the positive terminal of the battery is connected to the P-type semiconductor and the negative terminal of the battery is connected to the N-type of semiconductor. So in this case, the electrons flow from the N-type to the P-type. So the direction of the electron flow is from N to the P, and the holes or the positive charge carrier or the hole flow from P to N, and totally the current is flow from the P to N, or the current direction of conventional current is from the P to N. This is the direction of conventional current, but the direction of electron is from N to P. So in this case, when we consider alternative A, electron flows from P to N type, it is completely wrong. The electrons flow from N to P, not from P to A. Alternative B says the current cannot flow through the diode. If the diode is forward biased, we have the current can flow through the diodes. So this is completely wrong. The depletion layer increases, but if the diode is forward biased, the depletion layer always decrease, do not increase. And alternative D says the depletion layer decreases. So this decrement of the depletion layer allows the current to flow through the circuit. So the correct answer is on alternative D. If the diode is forward biased, the depletion layer decreases, the current flows through the circuit, and the electrons move from N-type semiconductor to the P-type semiconductor. This is CRO screen. So we have this signal diagram or the output signal on a CRO screen. If the time base is set to 10 milliseconds per centimeter and the gain control is 4 volts per centimeter, what is the period of this signal, or the period of the wave, or the period of the oscillation of this wave? So to find the period is always equal to the distance between the two crests times the time basis. The distance between two crests is given, it is simply 4 centimeter is given, or even we can determine it from the diagram. That means the distance between two crests or the distance between two throws. This segment always represents 1 centimeter on either sides. So then we can find it. So the distance between two crests is simply 1, 2, 3, and 4 centimeter, or the distance between two throws can also be determined in the same way, 1, 2, 3, and 4 centimeter. So the time base is set to be, it's equal to 10 milliseconds per centimeter. So this is directly equal to distance between two crests, or the distance to complete one oscillation or one full wave is 4 centimeter times the time base is 10 milliseconds per centimeter. So if we cancel centimeter with a centimeter, and 4 times 10 is 40 milliseconds. The period must be 4 milliseconds. So this is equals to 40 milli means 10 raised to minus 3 seconds. So we can write this number in terms of the decimal. So this is 1, 2, and 3. That is the period is equal to 0.04 second is the period of oscillation of the wave. So the correct answer is on alternative A. So which of the following diagram represents the LDR, or light dependent resistor? That means the resistor which its value varies with the lights, or the amount of the resistance is increase or decrease with the light. So on alternative A, exactly we see that this is a resistor, but we have some symbol like this here. This is what we call a thermistor. The resistor which its value is dependent depends on the temperature. As the temperature increases, the resistance is decreases with the temperature increasing. So on alternative V, still we have a resistor. This is also a resistor, but we have some arrow passing through that resistor symbol. So this represents what we call variable resistor, or in scientific name we can call it a rheostat. That means a resistor which can be adjusted. So on alternative C we have a diode. This is a diode but with this symbol. So this means that this diode is emitting light, so it's called light emitting diode. Or on alternative D we have the symbol with a resistor still, but two arrows are directed toward the resistor. So this is what we call the light dependent resistor, or LDR. So the correct answer is on alternative D. The symbol which indicate the light dependent resistor is on alternative D. So if this diagram represents a logic gates, combination of three logic gates, NOR, NAND and AND gates are connected. We have four inputs A, B, C and D, and here the output for A and B is E and the output for C and D is P. Then E and P uses as an input for A, these AND gates, and the output will become F. So if input from point A, B and C are all 0, A, B and C are 0, and the input from D is 1, then what will be the output from point E and point F? So let's do this logic gate by using this truth table. So point P has an input of C and D, so C and D is input of the NAND gate and P is the output for that NAND. So since C is 0 and D is 1, 0 and 1 is 0, but P is 1 because it is NAND gate. 0 NAND 1 is still 1. At the output E is the input for A and B, which is 0 and 0, but we have NOR gate is for this. So NOR is the opposite of OR. We know that 0 or 0 is 0. So but NOR is the opposite of OR. 0 NOR 0 is 1. We have here 1. But at point F uses input from P and E, or E and P. So at P we have 1, at E we have also 1, and we have AND gate is here and the output is F. So 1 and 1 is still 1. So the output at point E and F is are both 1, 1. So the correct alternative which combines these two value is on alternative B, which is 1 and 1. E is 1, F is also 1.